Here we go. Last video for section 3.3. Today we're talking about graphing logarithmic functions. And here's what the top of the page looks like. We're going to be graphing this basic function f of x equals the natural log of x. I want to refer you back to the first page of the notes from this section. And in that, we graphed not only 2 to the x here in red, but then we also graphed in green here y equals log base 2 of x. All of the logarithmic functions will have a graph very similar to this green one here. They will all have this asymptote that is x equals 0. And remember, that's because we talked about you can't take the log of a non-positive number here. You know, I can't put in 0 for x, for example, because you can't take 2 to a power and get 0. You can't take 2 to a power and get a negative number either. So no non-positive numbers can be in the domain of any log, whether it's base 2 or base e or base 10 or what. So they will all have this vertical asymptote here on the y-axis. They will also, all of the log functions will have this point right here, the point 1, 0, because as we talked about also the other day, log of 1, no matter what the base is always going to be 0. So whether it be base e, base 10, whatever, that point will be there. So that's kind of a basic start. So let's get those features drawn on the graph. We said we're always going to have this y-axis as an asymptote. We're always going to have the point 1, 0 on the graph. And again, that's because, you know, if I'm making my xy chart here, if I put in 1 for x, then my y value would be the natural log of 1, which is equal to 0, because base e to the 0 power is equal to 1. Now, the other key point that we're going to have on the graph, if we look back over here at our log base 2 of x graph, we had this point right here, which was the point 2, 1. And that was there because if you have log base 2 of 2, when the base and the number you're taking the log of match, then the answer is just 1. So we had the point 2, 1. For natural log, we will not have 2, 1, but we will have the point e, 1. Because if I take the natural log of e, that is equal to 1. The base and this number match, and so e to the first power is equal to 1. Now, remember, e is about 2.7 or so, 2.718, so we're here-ish. And then from there, we can just take our basic shape from that log graph on the previous page. We know it's going to look something like that. Now, I actually want to compare that to another base. Let's say I have g of x equals the common log of x, common log being base 10. You're still going to have this same vertical asymptote. You're still going to have the point 1, 0 because the common log of 1 is still 0. But instead of having the point e1, you will now have the point 10, 1 because the log of 10 is equal to 1. So that's going to be off of my graph over here, but it looks something like that. And so your log base 10, your common log graph would look kind of more like that. So in summary here, the two key points that are going to be on every log graph are the points 1, 0 and b1, where b is whatever the base of the function is. So keep those two in mind. Now, over here, I want us to do a little graph analysis, meaning let's find things like the domain. The domain of all of these log functions, if they haven't been shifted or anything, is going to be 0 to infinity. The range is just all real numbers, negative infinity to infinity. They're all continuous, so there won't be any holes or breaks in the graph. These are increasing. Remember, increasing meaning as the x value is increasing, so is the y value. There's no symmetry. The graph is unbounded. Remember, a couple chapters ago, we were talking about being bounded above or bounded below. This does not have any such boundary. Goes to positive infinity up in the positive y direction and negative infinity in the negative y direction. So therefore, there are also no extrema. All of these graphs will have a vertical asymptote at x equals 0. And then as far as the end behavior goes, you'll be able to write a couple of different statements. Now, for both of these graphs, so let's see here, end behavior. On the end out to the right over here, we can say the limit as x approaches infinity of f of x is equal to infinity, because as x is getting bigger and bigger, y is also getting bigger and bigger. The other end, though, it doesn't approach negative infinity. Actually, what's happening here on the left is these graphs are approaching x equals 0 from the right. So for those, we would write the limit as x approaches 0 from the right of f of x, and you can see there that the graph is going to negative infinity in those two cases. So that's the kind of analysis that I would expect you to be able to do for these. And really, no matter what the base is, these facts that I wrote down were true for base E and they're true for base 10. Where they will change a little bit is where you go to transform the graphs, which is what we're going to see next here. So it says in the example, describe how to transform the graph of f of x equals natural log x or common log of x into the graph of the given function. And here I kind of have the answers, but let's go through each one here. All right, fix this. Hold on. Here we go. All right, so the first one, we've got g of x equals the natural log of x plus 2. And so that is just taking the natural log graph, and if you add 2 to the x, we should be very familiar with this by now, that just shifts it 2 to the left. Okay, so if you see in this graph up here, it's in green, the natural log of x plus 2 takes the red graph, which was the basic natural log graph, and shifts it 2 to the left. So now instead of this point here being at 1, 0, it's going to be at negative 1, 0. Instead of the asymptote being on the y-axis, it's now going to be over here at x equals negative 2. So everything just shifted 2 to the left. This next one here is the one that is usually kind of tricky. You have the natural log of 3 minus x. Remember, this negative means that it flips over the y-axis. And then this plus 3 here means that you shift it 3 to the left. But you must do them in this order in order for them to turn out correct. So you will have, first you will shift it 3 to the left, and then you'll flip it over the y-axis. So if you look up here at the graph, if you can imagine taking this red graph, shifting it 3 to the left first. So this point would go over here, 1, 2, and it would be here, and the asymptote would be here like this. So it would look like this, but then flip it over the y-axis, and now you have this final graph that I have drawn here. Its asymptote, let me get rid of this here, it's kind of in the way. Okay, there we go. This asymptote is going to be at y equals 3, or not y equals 3, x equals 3. Like so. This point is this 2, 0 that you see here. Okay, now if I asked you to analyze this graph like we analyzed just the basic log graph, a few things would be different. First of all, you notice that it's decreasing. You notice that the domain on this one now is -infinity to 3. It's still continuous, it's still unbounded, it still doesn't have any extrema. For the end behavior, on the left, you would say the limit as x approaches -infinity of f of x is equal to infinity. But on the right, it's not approaching, x is not approaching infinity, it's approaching 2 from the left-hand side. So we would say the limit as x approaches 2 from the left of f of x equals -infinity. And so that would be your end behavior on that blue graph there. Okay, let's look at a couple more here. We've got 3 times the log of x, multiplying out in the front by 3 there. All that does is it's a vertical stretch by a factor of 3. So you take up here in this graph, you'll see the basic red graph, which is just common log or log base 10 of x. But then when you multiply it by 3, it stretches it out vertically. So on the regular common log graph, you have the point 10, 1. Whereas on 3 log x, you are going to have the point 10, 3, vertical stretch by a factor of 3. And then, of course, this last one here we see in blue, that's just taking the log of x and adding 1 to it. So that means you're going to shift it up 1 unit. And you can see if I just take this red graph and shift it up 1, then I get this blue graph, and there you go. Okay, I think from that you should be ready to go on the rest of the problems in section 3 on the homework packet. So you should be able to do 22 through 32, and that starts on page 7. Pages 7 and 8 are the graphing ones. Now on page 9, there are some word problems similar to what we've done before. You just have to plug the numbers into the formulas they give you. So I think you should be okay on those. So again, do the rest of section 3 in the homework packet. That would be numbers 22 through 32. All right, have a good one.